All right, so let's practice a tangent line question now with the product rule. And if you're particularly observant, you might notice that this is a quotient, not a product. However, I want to point out, I actually can rewrite this as a product because the thing that's in the denominator is a square root of x. And so, in fact, f of x is the same thing as x to the minus 1/2 power times the natural log of x. Now, I know what you're thinking. We know a sum rule. We know a difference rule. We know a product rule. Why don't we just use the rule for dividing? There must be a rule for dividing. And don't worry, there is. It's called the quotient rule. And it is coming. It will appear in the next section. However, the quotient rule is quite unpleasant, and you'll see why after we use it in a few examples. So anytime you can get around using the quotient rule by doing something like remembering that dividing by square root of x is the same thing as multiplying by x to the minus 1/2, it is in your interest to avoid using the quotient rule. So let's do this having rewritten f of x here as a product. Okay, so I'll write down my thing A, my thing B, and their derivatives. And I'm going to go ahead and notice I'm writing fractions in two ways here. One is with negative exponents, and one is as a literal fraction. It would probably make simplifying this easier if I wrote them all the same way. And given that an x to the 3/2 in the denominator isn't going to look that nice anyway, I'm just going to write everything here in terms of negative powers. So I'm going to write this x as an x to the minus 1. Just a different way of writing 1 over x. But it will make my life a little bit nicer. Having completed our tablet of information about A and B, we can go ahead and write down f prime. And so f prime, by the product rule, is going to be A prime times B plus A times the derivative of B. Okay, let me tidy this up a bit. X to the minus 1/2 times x to the minus 1. These are like bases, so I add the exponents. So I will get x to the minus 3/2. And it's worth noting here, actually, both of these things involve an x to the minus 3/2. So if I'm going to do any more work on this problem, it would be in my interest to factor out the x to the minus 3/2. Okay, and so that is our f prime of x. Again, if you left the derivative this way, it wouldn't be wrong. I'm just getting you in the habit because in the next section we're going to be doing lots of things where we have to solve equations with the derivative, and so it's a good idea to get used to doing some factoring with derivatives now. So that's our derivative, and it would have been pretty easy for us to forget by now that that's not actually what the question asked. The question actually asked about the equation of the tangent line. So to do that, I need to find the slope and the point. Let's go ahead and write down the point first. So I'm given that the x-coordinate of the point is e squared. And so I need to figure out what f of e squared is to fill in the blank. Again, remember if I'm finding a point on the graph, I need to plug the x-coordinate into the original function, not into the derivative. So I can plug the e squared in here. The natural log of e squared is 2. The square root of e squared is e. And so our point here is e squared comma 2 over e. What about the slope? Well, the slope I get by plugging the same e squared not into f, but into our formula that we found for f prime. And so following along here, this is going to be e squared to the minus 3 halves times 1 minus 1 half times the log of e squared. E squared to the minus 3 halves is going to be e to the minus 3 times 1 minus 1 half times the natural log of e squared, which is 2. But here you can actually notice this thing is 0. And so the slope of our tangent line to this graph at the point e squared comma 2 over e is 0. Remember, this means the tangent line is horizontal, which means that the equation for our tangent line is actually just y equals the y-coordinate here. Now, you might complain that I picked a point where it would work out easy for me, but let's go ahead and do it at a different point. So let's take the same function, and let's find the equation of the tangent line at, instead of x equals e squared, let's do x equals e to the 6th. Now, just as a little thought experiment, we've been doing a lot of work so far for this question. Relatively, you know. How much more work am I going to have to do to find the equation of the tangent line at e to the 6th for the same function? And the answer is, it's not actually going to take that much work. In fact, the work I'm going to have to redo is basically the same work that I have on this page. I still have to find the point, and I'm going to do that by plugging e to the 6th into my formula for f of x. The square root of e to the 6th would be e to the 6th to the 1/2. So those exponents would be stacked, so I would multiply them. And so the square root of e to the 6th is e cubed. And so my point here is e to the 6th comma 6 over e cubed. Likewise, to find the slope, I can plug e to the 6th into the derivative. We did find the derivative. It was there. So this is going to be e to the 6th to the minus 3 halves times 1 minus 1/2 times the natural log of e to the 6th. This will be e to the minus 9th, because again I have my exponents stacked, times, and now 1 minus 1/2 times 6. So this is 1 minus 3, and so that means my slope is minus 2 times e to the minus 9th. Okay, and now I just have to find the equation of the line. So I know the equation of the line looks like y equals negative 2e to the minus 9th times x plus b. I have to figure out what b is, which I can do by plugging in the point that I've been given. Well, the point that we found. Okay, so there's what it looks like after we plug it in. Let's go ahead and write all of our exponents of e in the numerator. So I'm going to write this as 6e to the minus 3. This will also be e to the minus 3. And so we'll discover that b is in fact 8 times e to the minus 3. And that gives us our final answer for the equation of the tangent line, which is y equals minus 2 e to the 9th x plus 8 e to the minus 3. One more type of example that I wanted to talk about in this section. And these are what I call derivatives with unspecified functions. And all I mean by that is that I'm taking a derivative of something with a function in it that I haven't specified. For example, here there's this f of x in the thing that I'm taking the derivative of. Okay. And so what's my answer here going to look like? Well, when I take the derivative of 2 times something, I get 2 times the derivative of the something, but I don't know what f is, so all I can possibly write is f prime of x for the derivative of f. And then minus the derivative of 7, which is 0, which means that my final answer here is going to be nothing but 2 times f prime of x. Any of our usual rules are allowed to pop up. So for example here, I have again my unspecified function f, and I've got an x squared plus 2x over here, and they're multiplied together, which means I'm going to have to use the product rule. And here, basically, all I have to do is all the work I know how to do. I know how to take the derivative of x squared plus 2x, namely I get 2x plus 2. I don't know anything about f at all, so I'm just going to write its derivative as f prime. And so then when I go to write out my answer here, it'll be a times f prime plus a prime times b. It'll just be times f of x. And try though I might, I can't really get this much simpler than this. So I'll leave that as an acceptable final answer. Sometimes these questions will themselves involve the derivative of f. So for example, you might be asked to take the derivative of something like this. So here I've got 2 times f of x plus 3 times, and then the derivative of f minus 4. And this is a perfectly reasonable thing to ask. F is a function, f prime's a function. I could take the derivative of this. Okay, and so let's do that. So we proceed along. Here's our thing A, here's our thing B. Here's the derivative of thing A. What's the derivative of thing B? Well, I need to take the derivative of f prime. And maybe you don't immediately think about what that's going to be, but the way we denote that is in sort of the cheekiest way possible, which is to just put another prime there, just to say, well, if you take the derivative of something, you put a prime there, so if you take the derivative of the derivative, you just put 2 primes there. And then this minus 4, its derivative is just 0, because it's a constant. Now, I'll note this thing here, the derivative of the derivative, it has a name. This is called the second derivative. It's going to appear a little bit here in this course, but if you go on to take the next course in this sequence, which is 141, it will show up a lot there. It turns out that this shows up a lot in physics in a lot of different ways, and also has interesting mathematical interpretations. Okay, but that aside, we can go ahead and write out what our product rule tells us, which is that this derivative is a prime, so 2f prime of x, times b, plus, and then a, times b prime. And that is our answer. I'm going to wrap up section 3.6 there. In 3.7, I'm going to pick up with our last derivative rule for the course, which will be the quotient rule, as we foreshadowed earlier. But I'm also going to take 3.7 as an opportunity to do a lot more examples of putting together all the different rules that we've talked about so far and all the different kinds of questions about derivatives. So you can really think of section 3.7 as being more of a review section with one tiny new thing and then a bunch of other pieces sort of put together. But that's all for now. I'll see you next time.